Welcome back, ladies and gentlemen, to another exciting chemistry video. Today we are going to switch our focus and primarily look at the concept of kinetics. And specifically today we are going to be focusing on reaction rates and rate law. So one thing we really haven't talked about much so far in this chemistry class is how quickly reactions take place. Some reactions take place very, very quickly, and some reactions take place very slowly. Well, how do we differentiate between them? How do we speed up chemical reactions? And how do we measure the rates of those chemical reactions? I'm excited to bring this video to you today. So let's go ahead and get started by looking at our learning objectives. We've got a lot of things we need to cover today. Now, this looks like an awful lot, but we're really only going to scratch the basic concepts of some of these chemical reactions. So we should be able to define kinetics, explain rates of change in chemical reactions based on stoichiometric coefficients, explain factors that influence rate law, use experimental data to determine rate law, understand how to write rate laws, explain reaction order, explain how to use graphs to determine change in reaction, calculate the value for rate law constant, explain the relationship between radioactive decay and first order kinetics, explain how elementary reactions function and how rate law can be determined from them, explain why 3 or more collisions are rare, explain the concept of a successful collision and why it happens, use a Maxwell Boltzmann distribution curve to analyze the number of molecules that have successful collisions, and label a reaction energy profile and determine whether a reaction is either endothermic or exothermic. So it sounds like a lot, but I think you'll get a pretty good idea of what we're looking at as we go through and complete each of these learning objectives. Let's go ahead and dive on in. So first, let's talk about the concept of kinetics itself. Kinetics is the study of how quickly reactants are converted into products in a chemical reaction. Again, some reactions occur very slowly, some reactions occur rather quickly. So by looking at the kinetics of the reaction, we can understand more about why reactions happen quickly or why reactions happen slowly. Now, there are several different factors that play a role in increasing or decreasing the rate of a reaction. And that includes increased concentrations. As we have more molecules are more likely to collide and therefore convert reactant into product. Agitation or stirring, which gives the molecules more energy, which means they're more likely to overcome the activation energy to be converted from reactant to product. Surface area means that there is more surface for the molecules to be able to collide, thus more successful collisions. Or catalysts, which alter the activation energy in order to speed up the reaction. So how can we determine how fast a reaction takes place? Well, what we are going to look at is what is known as rate law. Rates can be calculated by utilizing the basic form of the rate law, where rate equals K, which is a rate constant that's based on the reaction you are looking at, multiplied by the concentration of A to the power of X, multiplied by the concentration of B to the power of Y. Again, K is the rate constant. A and B, which are in brackets, are the concentration of the reactants in molarity, and X and Y are referred to as the reaction order. Now, there are several ways that we can determine the reaction order, and we will talk about those and how to figure those out in multiple different ways a little bit later on in the video. A little more about the rate law concept itself. The sum of the powers gives the overall order of the reaction, and the rate constant K differs depending on the temperature. So just a few more little pieces of information you may want to know about the concept of the rate law. So determining reaction order, let's take a look at what are known as elementary reactions. And when you think about a chemical reaction, a lot of times you just think in terms of these are my reactants and they are converted to products, and that's just how the reaction works. The two reactants collide and we get the products as a result of that chemical reaction. And in many chemical reactions, that is not the case. What happens is that the total reaction is actually broken down into multiple smaller steps known as elementary reactions. These are smaller individual steps of a larger reaction. And what happens is that when you combine these reactions together, what you get is the overall balanced chemical equation. So if we're looking at elementary reactions, the rate law is determined by the coefficients of those elementary reactions. So for example, if I look at the reaction here, I'm going to use elementary reaction 1 to determine my rate law. I would just simply write rate equals K times the concentration of O3. The reason it is to the power of 1 is because it is the coefficient of O3 in that very first elementary step. I'm not talking about the balanced equation on top, the elementary step underneath it. So you use the coefficient of those equations and they become the exponent. So if you're looking at elementary reactions, writing out the rate law is relatively simple. Just write the concentration of each of the reactants and take them to the power of whatever the coefficients of those reactants are. So again, very easy to go through and determine that. Now we can do a comparison of initial rates of a reaction and concentration to determine the reaction order. So if we don't have the elementary steps, we really can't make any assumptions as to what the coefficients are and what the exponents are going to be. So this is a multi-step process where we can utilize the information, we can utilize experimental data to determine what the order of each reactant is going to be. So the very first step here is to identify two experiments. That is, if I'm looking at those rows, where one concentration changes but the other does not. So for O2, I'm going to look at experiment 1 and experiment 2 going across in those rows. I'm utilizing those because NO stays the same, but the concentration of O2 changes. And so I compare the change in concentration, and what I notice is that in between the first experiment and the second experiment, the concentration of O2 doubles. It goes from 0.15 to 0.30. Now, in a similar way as step number 2, I'm going to determine what happens to the rate when O2 is doubled. So it roughly doubles. The rate also roughly doubles. So what I do is I plug that into this equation. I utilize those doubles. I think about them as 2. I solve 2 to what power is equal to 2. And whatever that power is, that is going to be your order for that particular reactant. So 2 to the first power is 2, so the order for O2 is 1. We would do the exact same method in order to determine the order of NO. So just as a way to follow up and finish up this problem, we want to figure out the overall order for NO and then the rate law and overall order for the entire reaction. So again, what I'm going to look at is I'm going to look for two rows, one where the concentration of NO changes, but the concentration of O2 doesn't. Again, the reason we do that is because we know that the change in initial rate is only going to be solely due to the change in concentration of NO when O2 stays the same. So we do that. We find that the concentration doubles in NO. Let's take a look at the rate. We notice that the rate increases by almost a factor of 4. So 2 to what power is 4? Well, what we would say is 2. So the order for NO is 2. So now that I know the order of NO and I know the order of O2, I can now write out my rate law. Rate equals K times the concentration of NO squared times O2. Once I figured that out, to determine the overall order, we just add all of the exponents together. So 2 plus 1 is equal to 3. So again, this is another way that we can determine the reaction order and be able to write out the rate law for this chemical equation. Another way that we can determine reaction order is by graphing concentration versus time. When we do this, what we want to look for is linear data. And we're going to look for it in one of 3 different ways. We take the concentration versus time, we take the natural log of the concentration versus time, or we take 1 over the concentration versus time. Whichever of those gives you a linear slope, as opposed to something that is exponential or something that is polynomial, that is going to be your order. And so if the concentration versus time gives you a linear slope, then it is 0 order. If the natural log of your concentration versus time gives you a linear slope, then it's first order. And if 1 over the concentration versus time gives you a linear slope, it is second order. One key interesting factor about this is that the absolute value of the slope actually gives you your rate constant K. So it's a really unique and interesting way to be able to calculate K and get your order data by being able to utilize graphs and graph concentration versus time in all 3 of these different methods. One thing that's interesting about first order, and you really want to keep this in the back of your mind because I noticed that a lot of questions that come up are directly related to first order because then they can ask extra questions about half-life. First order kinetics are directly related to half-life. That is the amount of time it takes for half of a material to radioactively decay. And the half-life is constant and related to K algebraically. You notice that as this reaction takes place, what I notice is that each increment in which the concentration is lost by a half is exactly the same. So for example, the time that it takes to go from 0.20 molar concentration of A to 0.10 molar concentration of A is the same as when it goes from 0.10 to 0.05. We're losing half of the amount each time. And we can relate K and the time that it takes to lose half the amount algebraically, where we can say that T1 half is equal to the natural log of 2 over K or 0.693 over K. Now your unit for your value for K is going to be 1 over whatever your unit time is for your half-life. So if I take a look at my graph here and notice that the time that it's occurring is in seconds, so if I were to go through and calculate the value for K for this, the unit would be 1 over seconds. So again, do keep in mind that we can utilize those graphs that aren't linear. For example, this is a nonlinear graph. We know that it's first order because we would graph natural log versus time and be able to get a linear relationship. But based on this graph here, we can look and figure out the half-lives and then be able to calculate the value for K and know its unit based on the formula that is listed down below. So let's talk about a collision model. The collision model basically refers to the fact that two things need to happen in order to have an effective collision to be able to convert our reactants into products. The first, there being a sufficient amount of energy to break the bond. So if two molecules collide with each other, but they collide with not insufficient amount of energy, they're not going to break the bonds necessary in order to convert reactant into product. However, if they are occurring at a faster rate, they have more kinetic energy, they will collide with enough energy in order to break the bonds in order for the reaction to take place to convert reactant to product. The other thing you need is proper orientation. What I mean by proper orientation is that the molecules have to be oriented a certain way in order to get the product that we want for our chemical reaction. So for example here, we're trying to get NO2 as our product, or at least one of our products. And if I look at the collision that's taking place at the very top, getting NO2 in its correct form is very unlikely if two oxygen molecules are colliding with one another. If I'm trying to get, same thing in the second reaction, if I'm trying to get O2, it's very unlikely that if that nitrogen collides with the central oxygen to be able to get an O2 molecule, it's very unlikely that that is going to take place. However, if the nitrogen collides with the O3 atom, the O3 molecule on the end, I'm very likely to get a molecule of NO2 and O2 from that. So that's what I mean by effective collisions, is that it has to be probable that we're likely to get our products from this collision, just simply based on the orientation of the molecules themselves. That and sufficient energy are important in order to get a successful collision. We can make a graph of the number of molecules and the amount of energy they have in a Maxwell Boltzmann distribution, which we've talked about in a previous video, and that can be used to show how many molecules have the proper amount of energy to overcome the energy barrier for a reaction to take place. So you see here, there is a line for the activation energy. Molecules that are further along in the graph have sufficient energy to overcome the activation energy for the chemical reaction to take place. Those molecules that are before that don't, and therefore those collisions will not be successful. Also notice what happens when you increase the temperature in a Maxwell Boltzmann distribution. We've talked about this previously. That the graph shifts to the right and the peak lowers. But notice that as the temperature is greater, the amount of molecules that have sufficient energy to overcome the activation energy is greater. So that logically makes sense that if the temperature is higher, we have more molecules with more energy above the activation energy barrier, and thus more successful collisions. The last thing I want to go through and talk about briefly is a reaction energy profile. And if you remember from your biology classes or perhaps even previous chemistry classes, you've probably talked a little bit about these before. Reaction diagrams show relative energies of reactants and products, the activation energy, and the transition state itself. The activation energy is the amount of energy added to start the reaction. So notice the arrow in the graph that shows the activation energy. That arrow is drawn from where your reactants start to the peak of the graph. That is how much energy is required to put into the reactants in order for the reaction to take place. The transition state you find at the peak of the reaction. That is where the transition is occurring between reactants and products. Now, this is a simplified diagram, as we can have reaction energy profiles that actually show elementary steps. So you might have 1, 2, or 3 or more peaks in a true reaction energy profile. Also notice the energy difference between reactants and products. You want to be able to draw that line between where the reactants start and where the products end. So the total amount of energy gained or released by the reaction is not drawn from the peak of the graph down to your products. It is drawn from where your reactants start and where your products are. So make sure you're able to identify and locate where those energies are located, as well as how to go through and label them. We can also, based on the information in this graph, determine if the overall reaction is endothermic or exothermic based on where my reactants are at the beginning and where my products are at the end. If I have released energy, my products will be lower than my reactants, and thus we would identify this as an exothermic reaction. If my products are higher than my reactants, then I would identify this as an endothermic reaction, one which absorbs energy, whereas an exothermic reaction is one that releases it. So as I mentioned before, there was a lot of student learning objectives, but we managed to cover quite a bit of information in this particular video lesson. So I'm not going to go through the student learning objectives again, but I hope you enjoyed the video. Make sure you like, comment, and subscribe. And got a whole library full of chemistry videos you are more than welcome to watch. You can even leave them on loop if you want to in order to bump up the watch hours. Hopefully YouTube doesn't ban or modify that. Anyways, have a great day. We will see you soon, and we will hopefully talk to you later. Have a great day. Bye.